Okay, we spoke about borrowing strengths, for instance, in medical studies. I have brought a citation with me. It's from a paper in the Pharmaceutical Statistics journal. There's also the name volley involved, but it has nothing to do with the imprecise probability volley. Just to mention this. Okay, as an argument to go in this direction. Yeah, questions which could arise. The knowledge truly precise enough? That was the question before. So to say it's quite easy to have the idea that it's important to bring knowledge about the blood pressure into the argument. It cannot be more than 250 and not below 100. But does it specify a distribution? How should we express ignorance? If we want to say we don't know, we don't basically know anything about the parameter, a little bit strange, but sometimes this is understood as a kind of compromise. So if you have different people saying different things, so it could be also a way to stay ignorant. One could also try to build in partial knowledge, again, knowledge which is not fully specifying distribution. And what to do on the prior data conflict? That's, I think, also quite important point. It fits to the point we have raised before here. What to do if I have assumed a prior, borrowing strengths, and the prior is, so to say, wrong. The prior tells me the data live here, and I observe data just over there. And all the measurement is fine, so I don't have outliers. What shall I do? Bayesian statistics basically tells me to take the mean. But what should I do? Could one construct probability models which warn us if we have such prior data conflict? So maybe telling us that we have to be cautious in our decision making. How could such a distribution look like? So I don't know if somebody has thought about the uniform distribution as a non-informative prior. There are some arguments against this. Particularly if you don't know anything about SIPTA, you also don't know anything about SIPTA squared. But on the other hand, if theta is uniformly distributed, SIPTA squared is not uniformly distributed, so there are some kind of contradictions. I expected previously to say something about this, so I put this argument on the slides. I think it's just something you can read. So I tried to be precise in my mathematical formulation. So taking the uniform distribution typically does not mean we don't know anything. There are in Bayesian statistics ways to counteract the trick I use. So-called Jeffreys prior bias, but they are also somehow counterintuitive. I think it's really difficult to give a probability distribution telling that you don't know anything. Every probability distribution gives you some information, I would say. One could argue in that objective Bayesian way we had discussed before, But even if it's not uninformative, it's in some sense minimal informative, or it's a kind of standard choice, etc., founding your inference that could be a way out. But still, I think it's difficult to understand, to have just the distribution to express uninformativity. So this is more technical. I just skip it. So, and now to the topic of prior data conflict. What to do if prior information and outlier free sample information are conflicting? Especially when the sample is too small to rule out the effects of the prior distribution. I brought this quotation again. It's by Ivan and Marshonov in the Bayesian analysis, like the prominent statistical analysis, statistical journal, focusing on Bayesian statistics. If we can show that the observed data is surprising in light of the sampling model in the prior, then we must be at least suspicious about the validity of the inferences drawn. So we do something, we do calculations, but we remain suspicious about the results. What's the scientific status of a result you don't believe in because you're suspicious?
What do we mean by sampling model here?
We would change the sampling model. So we could do maybe resolve the conflict, but basically note that you have a whole bunch of sampling models, so to say, that you have a certain parameter, so you have all the normal distributions. For instance, as your basic sampling distribution is unknown mean, so you're basically covering the whole little line. Because sometimes it could help with that kind of bimodal distribution, and you know that you cannot fix this normal distribution, which is unimodal. So what else can we do? And I think it's quite an interesting topic. Typically in sociology, it's quite often happens that people do statistical analysis, very proper, sophisticated statistical analysis, and then they calculate the results, very precise, to the 10th digits, and then they don't believe in the result because the data are messy and the situation is too complicated. Is there something where we could do better? Statistical framework which gives us some kind of reasoning where in certain situations we become cautious in our conclusions. For instance, if we use its distribution in decision making, we should somehow be more cautious in decision making based on this distribution compared to the situation where we have complete agreement of our prior assumptions and all what we have observed. Has somebody an idea how a more cautious distribution could apply? So I give you a probability distribution, and you give me back a more cautious one.
So there is a folklore theorem that says that people are typically more overconfident that they should, right? And the folklore is about factor of 3, so multiply by 3 the variance.
Yeah. bit of psychology into the argument.
I heard this argument by Jim Berger. So
Okay, I didn't know that Berger uses it like that as well. Okay. Very good. Anybody else? I would say it's, you all have given the correct answer. I think there is no such precise distribution. So you may think a little bit how you would do it with imprecise probability. You have a set of distributions. You observe something which is conflicting. What happens? The set gets larger. You observe something which is in great agreement. The set gets smaller. Very natural. And when you do this decision theory with all these criteria Teddy gave you, the Maximilian criterion, you are more cautious in your decision. It's not easy, as I'm saying, so there are skeptical bases in the background based on the scalation topic, where you always get to say more imprecise. There is basically an issue of design of experiments. But I still very much favor the idea that one should construct models. They have this effect. If you start with a set of models and you have prior data agreement, then the set of posterior distribution becomes smaller. And if you have prior data conflict, the set gets larger. So I later on will construct such a model. Good. Yeah, how to be cautious within classical probability calculus. And that was the question. I had expected somebody to come up with variance as an argument, saying huge variance, then you could be more cautious. Yeah, maybe it's too much for the variance to take into account variability and also conflicting information in the same moment. And I also will present later on models that make that more clear, I hope. So that's the tour through classical statistical approaches. And I now want to just come into imprecise probability for statistics, some first ideas. I decided to be very non-technical, so I just put some slides here, picking out some aspects of imprecise probabilities which could be helpful later on. Yeah, so it's just 10% of things you heard before with Gert and Teddy, but maybe it's just helpful for statistics. Good. So imprecise probabilities for statistics. Yeah, I think generally, as a statistician, one is a minority. One is in the minority if one argues for the use of imprecise probabilities. Here it's, I think, a very small minority. So for most statisticians, still the idea of using imprecise probabilities is something strange. Which is, yeah, we have to wait for the younger generation to take up things with their enthusiasm and their fresh view. So in statistics, it's still a little bit iffy situation, which is quite surprising because many important people shaping the theory of imprecise probabilities, Peter Walke, With Weissenberger and Teddy Seidenberg, also Dempster, they are genuine statisticians. So basically, the main motivation was statistics, statistical inference. Dempster is extremely famous in statistics, for instance, for having invented the EM algorithm. In his paper is 20,000 citation or something like this. Still, he thinks his generalized inference theory is his major contribution. But in statistics, yeah, maybe. So maybe times change. Maybe a little bit contributed to the whole situation has the name imprecise probabilities. It's an old discussion. So indeed, from an advertising point of view, it's a rather big foul to call a theory that claims to be more precise in the sense that you have more flexible models, that you can have more powerful conclusions, to call it imprecise. But that's the historic tradition. So, very, very quick going through this, basic on a very intuitive understanding. Basic quantities are agreed sets. So sets of probability models, classic probability models, which are somehow related to interval valued probabilities, probabilities with a lower bound and an upper bound. The one-to-one relationship is mathematically wrong, as you know from Gert's talk. You also know from Gert that the area of imprecise probabilities, expectation offer more flexibility than just probabilities. But nevertheless, to have an intuitive feeling, we just takes this. So instead of a real number, you get an interval as your probability. And similar as probability, classical probability has to satisfy some rationality conditions, basically summing up to 1 being greater than 0. Although these intervals or the non-additive set functions involved should satisfy certain properties. And quite crucial, I think this cannot be stressed enough. Teddy said it, Gert said it, I say it again. Take these sets as the basic entity. So the set as an whole, the interval as an whole. No mixing. So as a Bayesian somehow has the idea that if a prior of the second level and mix everything, and then I get how likely the elements in the interval are. And it's a precise probability, which is self-constructed in a much more complicated way. So it's a good training for doing probability calculus, but it's a long way to model. So you have to get out, in some sense, of this classical probability thinking, take the set as an entity of its own, just like a chemical element, which is also just defined by the connection of all its parts. And you cannot leave away certain atoms or, dispose them separately or something like that. So that's an important point of view. If we take this seriously, under obvious misuse of mathematics, we can have the idea of the size of a set. Because a set of probabilities is typically infinitely many large, so the term size is a little bit wrong. But still, you have this kind of order. If you have one set, you can say another set is larger in the sense that it contains the previous set, or smaller, being contained, or being incomparable with the previous set. So you have some ideas of size of the sets. With an interval, it's basically the same. You can have intervals of different lengths, and that's so to say a fundamental modeling idea. As an extreme case, you have traditional probability, the situation of full information where you just get one single element. So if all the bounds of the interval just shrink to one point, and this point satisfies certain conditions, then you have a classical probability. So it's clearly contained as a special case. On the other hand, Gerd, you are smiling. What should I say? Okay, he seems to be distracted. Good. On the other hand, on the other end of the continuum, probability 0, 1 for non-trivial events. Set of all probability measures on the other hand. So it's the perfect way to express complete ignorance. This means I don't know anything. And it's easy, basically, to formalize. So this is some first basic notions. Yeah. And so I would like you to take 5 minutes, maybe even a bit more, depending on you how long you need, and writing down whether this idea could somehow help in things we had before, in things you had been interested in things you will be interested in, whatever. So just going to this more general idea of intervals, of sets, what could it be in statistics? And I will try to resolve the technical things here. It's not an entertainment program for you, okay? So you don't look to me, you look on your papers, right? Maybe we could also
do you want to like image me?
no, I just look for breakout rooms. But this was not. Unfixierte Kontrollleiste. So we have it. So now it looks better. Good idea. When you are not sure, discuss with your neighbors.
No, sorry. Yeah,
So, sorry for interrupting you. Somehow discussing very intensively. Others are going to Bristol a little bit. So maybe let's turn back for the to the plenum, so to say. Yeah, I was criticized fully correctly that the word complete ignorance is a little bit misplaced here. So still, of course, you specify a measurable space and that things you specify a basic model, and so maybe complete is wrong. It's also difficult to make conclusions from really the whole interval 0, 1s. What is in the slide is a construction of a model that is called near ignorance model. Basically fills in from the inner this range of 0, 1. But now to you, who likes to present or say something? Say something.
Yeah, well, for example, I think in the Bayesian context, you can take instead of one prior, like a set of priors, and then complete a set of posteriors.
So in Bayesian analysis, we take a set of prior. Seems quite natural. I just repeated what you said for the Zoom. Yeah, we take a set of priors, get a set of posteriors. No, certainly have some kind of robustness involved. That's basically what these robust Bayesian people do. Looking at the feeling how prior is working, and so this is more robust. Good idea. Also can maybe govern the amount of knowledge, having a larger set. This is a difficult situation. The financial market, like in Indonesia, anything about this country, in England, market, European Union, for instance. Okay, very good. Other topics you were intensively discussing? No?
Yeah, I mean, so we were discussing how you could make use of this in terms of frequency statistics for automation, and we got into a discussion of whether it would make sense to think about the long-run frequency as not converging, like not being
Very good.
but like also like Imprecise. And yeah, we get into a bit of a question of whether that is the some sort of interpretive possibility, but like so that was
Very good. So it's there's one person, Terry Fine, who basically dedicated more or less his life to this question how you could establish some frequency strings. Gerd was presenting something on Monday afternoon on this topic, and of course it's quite natural. It's complicated, but also quite nice. The first paper having done this is interestingly by Peter Woolley and Terence Boyne. It's 1981 in Journal of Statistics. Woolley started a step into imprecise probabilities, also by first looking at frequency models and then turning to more Bayesian-like models. Just if somebody knows the idea of von Mises collectives from frequencies construction, several students are fine who try to develop this among Dr. Marco.
So I don't know if you have time, but maybe say a bit about how these size things that I interpreted, because the complaint we're having is that it makes sense that we are philosophers and we're going to statistic, but it makes sense to me to, or to some extent, it makes sense in the Bayesian framework to see the imposition as representing sort of how uncertainty about the present way. But if you think about it in a frequency framework, where it's basically the infinite, like the long last frequency, like the implication of that being inside. It's more difficult for me to like understand what that would mean and to say something.
It's definitely more complicated,
Yeah.
but on the other hand, it's also more hard to be argued away. So Bayesian imprecise stuff often that kind of epistemic thing, and if you have one day it's here, you can show that you really have some frequent meaning of real imprecision. And these, in the long run, we just limit up to say about these bounds, and it's a way to discuss. And it's also quite an interesting way for statistical modeling. In many statistical modeling, you have such things which are called unobserved heterogeneity. That basically means that you have repetitions, but small individual variations. So you do a medical study, and basically all study participants have the same distribution, basically, but it's a little bit different due to genetic dispositions you cannot observe. So you have, if you look at it from a long frequent perspective, you also have oscillating relative frequencies. And that's a very powerful way to model some observed heterogeneity, for instance, in econometrics. So,
If we have a sequence which doesn't converge and oscillation, the interval wouldn't be a convex area. So we have imprecise probability, but we can't.
Typically, then you're doing something continuous, taking the sum of or the average of some long sequences. It's typically so the sum over something is a continuous function, and then you typically have exact or intervals. So first, I could imagine, having two different types of distributions and this is done. So this type, this type, this type. And you will get two different limits in the end.
Yeah, related to this, I was also concerned for the Bayesian model, whether it would preserve the truth convergence. Because if you have this dilation phenomenon infinitely often, then can block this.
Can, but it's Teddy would always say it's a problem of the experimental design. Look at the patient and avoid dilation. It's a way of human ignorance. On the other hand, it may be related to update. Maybe if you have sets of probabilities, maybe updating also means you throw out certain elements that don't fit to your data and sometimes. So you're not just calculating step by step the posterior distribution, but you involve something like, so to say, a likelihood principle in between, that you just look to the source priors which fit better to the data. Then in some situations you can avoid it. Okay, further comments?
So I think another way to include it's modeling for the frequentist case would be to consider contamination models, where you have for your density function by some quality epsilon ball around the function, and for the R probability is with just which I ignore to find this epsilon ball, and then you have a set of density function for which you can infer some parameters, and a set of parameters and several conditions.
When we get to something which was a little bit detailed slides coming, so that you have sort of models that you think of instead working with a normal distribution, you work with distributions that are somehow close to, almost to. And one way to formalize it is the epsilon contamination model, where you think that 1 minus epsilon of the time the distribution comes from the, so to say, ideal model, and in epsilon cases everything. We have children typically very nice, but if anything goes wrong, completely out of it. Okay. So this is it's a frequentist way to go. It's also a Bayesian way to go. So there's some work by Werder who uses epsilon contamination models as prior distributions. A lot of the calculations simply by considering. So something that one can do some calculations even by hand. Teddy?
I was just going to suggest that when you have interesting models, there are different ways of characterizing them. From the IP purpose to the epsilon contaminated model, there's a wonderful IP characterization. This you have a space, and we can assume the space is atomic because the elements of the space come from this partition. Suppose I specify my model directly in an IP way by giving lower probabilities for each of the atoms. I say that's all I'll tell you. That is equivalent to an epsilon. I specify lower probabilities for each element of my fundamental partition, the atoms. I don't say anything more. That is equivalent to this epsilon contaminated model, which can be thought of as a neighborhood model around some specific distribution. So I mention that only because it brings out the fact that these models have multiple characterizations, and when you look at them from IP framework, they have their own footprint, their own way of being stated in IP models, which doesn't commit you to this frequentist understanding of being the neighborhood of a special objective probability. Because you're saying, I'm just giving you lower probabilities on the atoms. inside a die, the probability of each element of each outcome has a lower probability. I give you that, assuming this doesn't sum to one. If it sums to one, I have a precise model. But if it sums to less than one, I said it's okay. So I think what the machinery of the IP does is allows us to look at some familiar statistical models and see them through an IP frame perspective and allows you to score them. I mentioned that only for the epsilon variable model, very simple. But I think that's one way of using it.
Very good point. Yes.
Just wanted to add that you will probably remember from the first day that I gave you on a two-element space. I said that all the coherent models were these epsilon contaminated models. The reason is there's only two atoms on the two, and everything specified by the lower probability on those two atoms. So what Ted just said is a way of seeing why I said that there's only one type of coherent model on the two-element space.
So in some sense, they are the first step into it. By the way, this historically happened in the frequencies framework. So people working on robust statistics, the first IP models they used to adjust these epsilon optimization models. Good. Further? Okay. Sure. Very good. So thank you for this. Yeah, I just also collected some things. We had this discussion yesterday with Terry. So just take a set as different experts with different precise probabilities. So immediate way to step into sets of probabilities, because as we had earlier, just don't mix these probabilities. You will destroy their basic meaning. We had Definiti's fundamental theorem yesterday. So just take certain events where you know the probabilities and leave the rest to the theory. By general theorem, Terry showed yesterday, you get out rigorous imprecise probability model, and as a tried also rephrased yesterday, it's for instance very convenient for expert systems. They have where sample space is extremely big. There is no need to assign probabilities to all, for instance, atoms of the sample space. Just use these events. For instance, your medical experts have an idea of the probabilities and then leave the rest to the calculation. There is a group in Harvard currently working on multi-resolution inference, where I think your data come into, so to say, different resolutions. It's also basically a way of applying this fundamental theory of probability. And if you are spoiled enough by imprecise probabilities, of course, you won't assign precise probabilities to the events, you will assign imprecise probabilities to events. Still, the theory helps to get the coherent extension out of it. So in contrast to classical probability, where you have to have certain properties of your generator assigning your probability distribution, you can just assign any subset of the algebra, and there is a unique extension to imprecise probability. Yeah, similar to this individual evidence, this Ellsberg story we also had discussed yesterday. I would say, I would claim that these intervals allow for a very natural way of modeling partial knowledge, just takes interval and the probabilities, and yeah, write down what you know. In psychology, there was a longer branch of research where one tried to construct probabilities by, so to say, ordinal probabilities. There was the idea that you have this quite often in psychometrics, that for normal people it's much easier to order things than to give numbers to people. So they got a series of events and they had to order them, which event is more likely than another one. There is, you have to do enormous amount of mathematics around it and continuity properties and all these things to get out the precise distribution you very naturally get. Just describing a set of distributions. If you have certain events incomparable, fine, leave them out. Again, you get a set of distribution. You have this approximately two models. Julian was mentioned, unobserved heterogeneity, also mentioned in the reply. Also would like to come back to this interval ordering. So you have can express that one interval is containing the other one. If this is for every event, then you can say one assignment is more cautious than the other one. It's a very natural way to describe this cautiousness. You can describe learning under homogeneous information, at least in some standard models where these intervals get smaller. You can describe, at least in some standard model, the modeling of conflicting information, intervals get wider. And something I personally like very much, you have that it's a little bit difficult argument to be brought up shortly before lunch, but in classical statistics, you have a uniform distribution. In the discrete setting, so sampling, you say all probabilities should be equal, all probabilities of atomic events, of elementary events should be equal. Okay, then I know the probability. It's 1 over the cardinality of the underlying space. Sometimes you have, this is a very strong symmetry argument, but in practice, you quite often have different kind of symmetry. You could have a symmetry because you know that there was some mechanism in the background which was built up to do symmetry. So you have an official lottery where official people observe everything, that all the balls are equally weighted, etc. So you really have symmetry. And when I tell you that today there is a derby in Jakarta, where the first football club plays against the second football club, who will win? You probably also are symmetric in your information. You don't know anything why team 1 should be better than team 2. But this is a completely different kind of symmetry. Some people call it, so to say, negative symmetry. It's just the absence of asymmetry. So you don't know that there is real symmetry, you just don't know anything which is in favor of asymmetry. And with imprecise probabilities, you can express this very easily. So you have probabilities, if you have this perfect symmetry, you go back to the classical model, 1 over the cardinality of the sample space. If you have less symmetry, there are a lot of ways to express the information, the probabilities are equal without restricting to this precise classification. And I think that's quite a convincing thing. If you remember, partially statistically oriented, that the whole sampling theory is based on uniform distributions, I think it's quite a nice thing to develop, because basically in almost any social survey, you don't know perfectly this selection probabilities. So that could be also something which would be interesting to continue. Okay. Yeah, imprecise probabilities allowed to express quality of information. It's something which should be stressed again and again. There is a recent paper by Robin Gong, who also was mentioned by Teddy yesterday, and Charlie Meng, with the title, "Let's be imprecise in order to be precise," about what we don't know. And I think that very well summarizes this idea that imprecise somewhat less quality of information. Good. Oh yeah, I should mention also this, because in imprecise world there are several updating rules. It's something, or conditioning rules. It's also something Teddy mentioned yesterday. When you look at the more general framework, you also get an idea that quite different things are collapsing in the classical framework, different notions, etc. And of course, you can, if you generalize them, then you get also different ways to update. The standard way is the so-called generalized Bayes rule. Most people working in this area use it. It's basically conditioning element by element. So what one typically would naively do. So this is this robust framework. It can also be justified in a very rigorous way from generalized coherence axioms. This is basically, so to say, done in the second part of Wallis' book. I would like to come back again to this paper by Gong and Meng. They discuss a lot of statistical paradoxes in the context of these updating rules. I think it's really quite nice paper. Okay, that's this quick tour to some aspects of imprecise probabilities. And questions so far? Okay. So I would use remaining time to become a little bit more concrete. Maybe something which was a little bit disturbing for some of you was many things were, to say politely, mathematically very sloppy. I spoke about intuition versus formalism, etc. So my motivation was just to give you some ideas of these things. I think, but now the point has come, really should at least try to make some things a little bit. Okay. This probably are slides which are not so perfectly suited for everybody, but I hope that nevertheless I could give you some idea what's going on. So basically, I will speak about topic 5 and topic 7. Yeah, and I give you the slides so you can also have a look at topic 6. Okay. This is the question. It's also applied Bayesian models. We'll discuss it in the frequent setting. Two small differences matter. So from a statistical modeling perspective, somebody working on imprecise probabilities is just so to say, a masochist who makes everything more complicated, just to have to work with a more complicated mathematical framework. But the question is it really needed? Of course, we know that every scientific abstraction process means that one leaves ways certain aspects, that one takes things as the same, which are not perfectly the same, etc. It's the effect of every categorization in science. But two small differences matter also situation where we really have to be careful. So from a precise probabilistic perspective, there is this very famous saying by Box and many described Box. Essentially, all models are wrong. So it's just what I said before, it's a matter of modeling building that you leave away certain things, but some of them are useful. So let's take the useful models and work with them in statistics. So no issue in assuming, for instance, a certain distribution if it makes it more convenient to calculate. This implicitly assumes a kind of continuity which I would like to doubt for a moment. So, are there situations, I ask, where we have probability models, where model 1 is very similar to model 2, so to say? But the conclusions one can draw from model 1 are quite different from conclusions drawn from model 2. And to motivate this, I would like to start with this distribution. So, as you know it from many applications, regular bell-shaped density. Do you have an idea what this distribution is? So it basically looks very much like a normal distribution. It's not a normal distribution. It's a little bit different. It's a so-called Cauchy distribution. I depicted both densities. So the dotted line is the Cauchy distribution. The other one is the normal distribution. And from a modeling point of view, you would say, yeah, of course they are different. Who cares? So there is in statistics this saying, they even have seen a worse normal distribution. So you can always, at least in some situations, assume normality more or less. If you do statistical inference, let's do the most simple one. Inference on the location parameter. And we take the most simple statistical procedure ever, the arithmetic mean. So if the data come from the normal distribution, let's assume we know this shape parameter. If they come from a normal distribution and we take this arithmetic mean, then it's, as we had with this fiducial argument, it's distributed again with a normal distribution around the true mean, and we have a variance of 1 over n, sigma squared over n, which means that the more data we have, n is the sample size, the more data we have, the more concentrated gets this distribution around the true value, which basically means learning in the classical statistical sense. So you have a more and more higher probability to be very close to the true value. If you do the same for the Cauchy distribution, then you take have again that x bar is based on single Cauchy distributions. It's again Cauchy distributed, but you have again this location parameter, but you have a scale parameter which does not change with n. So it remains 1. Very simple formula, but what does it mean? In the last situation, you cannot learn. Whether you have 100 data, 1,000 data points, or 1 billion, you always have the same distribution and just looking at one person. So all intuition you have about learning in a classical statistical way breaks down in this example. So increasing the sample size does not help anything. You can collect as many data as you want. You are as unstable as just picking up one person. You completely break down. And that's the difference between these two distributions. All models are wrong, but some are useful, etc. This was the starting point. I prepared also a simulation to show it in statistical testing. You get the same catastrophe, also the statistical tests. You get the statistical test in the end with when you do a 5% test, you get true error first kind of 95%. So the test also breaks completely down. Due to time, I would like to skip this simulation and come to kind of solution. So this example is very well known. So it was the starting point of a branch in statistics in the late 60s, early 70s, robust statistics. And the idea was that one just should try to insure oneself against such effects. So basically work with approximately true distributions, distributions which are in some neighborhood of the normal distribution, and then proceed. And this allowing for different small variations in the form of the distribution, this avoids such disastrous conclusions. So you lose a little bit in efficiency, but basically you gain a lot in working with this model, and these are imprecise probability models, basically. There is a recent survey on neighborhood models written by Ignacio Montes, Enrique Miranda, and Sebastian de Sterk, which really is worth reading. You get a lot of impression about these models. So once again, neighborhood model take a set of distributions which are close. This can be topologically formalized, close to your ideal distribution underlying distribution and then work with this set. We can build up, in particular, statistical testing theory based on this. This is called the Huber-Strassen theory because it's the first famous paper in that direction. It's written by Peter Huber and Volker Strassen. Here's a description of these models. They take a general form. I skip it due to time. I would just maybe say that the ideas also are getting attractive in machine learning. The first guys who used neighborhood models in machine learning are, to the best of my knowledge, Abelan and Moral. They had the idea that you work with an epsilon contamination model in a classification tree, not taking your observations, so to say, fully seriously, that avoids overfitting. So a basic problem in machine learning is that you basically copy the data and give too much structure to what you have observed. And by going away from this, you clearly can avoid overfitting. These classification trees are amazingly good. Yeah, and there's a lot of work continuing in this idea, where you try to take neighborhoods of classical models also in machine learning. Maybe also to summarize models and make them better interpreted. So I will speak 2 minutes about Bayesian inference. So what I basically wanted to show you is some classical Bayesian learning with so-called conjugated models that you calculate you take your prior, you calculate the posterior distribution. Once you have this posterior, you get new data and you calculate the new posterior with the previous posterior as the new prior, etc. And so you update this step by step. It can be done very elegantly, and this can also be generalized to IP, imprecise probabilities. It's the background, technical background of the very prominent paper by Wally. I cited at the beginning, so Wally 1996. There's just this inference for categorical data. So you have data that just have categories, so no natural order, and you do a generalized Bayesian inference on the number of categories, basically, or the corresponding predicate distributions. And this is probably the most powerful IP model. And machine learning to build on it, because you typically have categorical data and classification problems. We can also extend it to other distributions, the so-called exponential family, technical device, summarizing standard statistical model. Gerd, together with Eric, was the first one who looked at these more general models. Yeah, and one can build step by step on it. And I included the way of modeling prior data conflict. That's something which is more or less important for me. So you have here a set of distributions depicted by drawing the distribution functions. And this triangle gives you an observation. So if you have an observation which is in accordance what you have expected as prior distributions, the posterior gets smaller. If you have an observation which is in contradiction to this, what you expected as a prior, everything explodes. That's just the behavior I would have liked to see. And indeed, it can be done with these canonical exponential families. So now, the last 7 minutes, and I try not to use all 7 of them, turns the view a little bit around, and I should speak about data. A strange presentation about statistics. The data found in the last 7 minutes, but we have to wait. Goes. So I quickly would like to guide you through my slides. And so forget for a moment about imprecise probabilities. We soon come to something similar. So when you have normal statistical inference, classical statistical inference, so you have some uncertainty in your sample, and under regular model, not containing the Cauchy distribution, as you know from now, you have this idea that this uncertainty gets smaller and smaller the more data you have. This is a kind of uncertainty which gets smaller, but there is also a kind of uncertainty which does not get smaller when you have more data. So if you think of a standard statistical regression model, and now use this XY notation, not ZY as before, and your data are not coming from the variables you're interested in, but from some related variables, because you may have measurement error, for instance, then you have the situation that you have an error which does not decrease with increasing samples. So when you have 100 data points and they are mismeasured, you have a measurement error. When you have 1,000 data points and they are mismeasured, you still have a measurement error. And when you have 100,000 data points, the measurement error is still the same. So it's a kind of uncertainty which does not vanish with increasing sample size. And I would like to call this big data uncertainty, just for advertising reasons. So to say, yeah, everything is big data. So why should we not have a big data uncertainty? And I think that term fits very well, because it's uncertainty which is still even in big data. If we have a stream of terabytes of measurement points, if they are wrong, they are wrong. Even if there's billions of billions. Okay. What does statistics do in such situations? The silly solution is to ignore this error. A little bit more sophisticated solution is to try to make models to integrate it out. So you make some so-called deficiency model relating the observed variables to the ideal variables, and then under certain assumptions you either can construct corrected likelihood functions, or also in a Bayesian setting you can do certain corrections, and then you somehow get into a feeling, or you can correct for the measurement error. The bad thing here is that you make assumptions, so to say, on things you cannot observe. You make assumptions on an ideal quantity which per definition as an ideal quantity cannot be observed. So everything depends on these assumptions. And instead of, for instance, assuming a normal distribution in a normal statistical setting, where you can test whether it's a normal distribution, you don't have any chance, at least if you don't have replication data, to test whether this distribution model is true or not. And the big question is what to do. Probably getting you to lunch, but I want to provide a solution quickly. There is, you make assumptions and maybe I can show, no, I cannot show this. I have an example showing that you cannot, for instance, test between missing at random and not missing at random. So when you have missing data, it's very similar to missed measurement data. I have simulated here. A situation, here you have a distribution, so to say, of the observed data. From which distribution is it coming? So you have 10% measurement error, missing data in this distribution. Of course, it could come from this. It's one situation. Indeed, I simulated it from this. So you don't have any chance to conclude on the process in the back. And there is a theory around which is somehow related to imprecise probabilities, which goes with Charles Mansky. He has formulated this law of decreasing credibility, that the credibility of inferences decreases with the strength of the assumptions maintained. When I have to put a lot of assumptions into a statistical analysis, then I'm running into danger that nobody trusts my results. And what he suggests is to work with a set of models that are compatible to the data. And that's very close to an imprecise probability. So not make assumptions until you have a precise model, but take the situation as it is and work with a set of all models compatible with what we have. That's the whole story with Charles Mansky. So I think to conclude, IP, including partial identification, offers substantially new opportunities for sound statistical inference and modeling. So much yet to develop, explore, and apply. So we need young, enthusiastic, clever people to do this. So bring in your enthusiasm and your expertise. Yeah, and enjoy your excursion in the afternoon.